Good morning to all. Today we are going to study about the last topic in the Unit 3, which is timing and delays. See, for any digital circuits, timing and delay are very important factors. Basically, the programming part, where we want to know how much time it requires in order to finish execution of a program. See, for digital circuits or for any microprocessor circuits, clock is a very important part because we require clocks in order to perform any action, any instruction execution, any fetching, any decoding. We want a clock pulse to be given in order to do any functionality. So, in order to understand how the timings are being generated and how the delays are being calculated for the execution of an program, we are going to study in this session. So every instruction requires a certain amount of or certain number of clock pulses or clock cycles for its execution. Contains some number of clock cycles. So what is a clock cycle? One clock period, nothing but high and low pulse. High pulse, low pulse. Combination will get as one clock pulse. So every instruction requires a definite number of clock cycles for its execution. The duration required for the execution of an instruction can be used to derive the required delays. The duration required for execution of an instruction can be used to derive the delays. A sequence of instructions, if executed by a processor, will require a time duration, that is the sum of all the individual time durations required for execution of each instruction. So if you have a sequence of instructions which are being processed, which are being executed by a processor, the total number of time duration taken by the corresponding program is the nothing but sum of all the individual time durations required for execution of single instruction, each instruction. So when a loop instruction is used in the program, the number of instructions in the program may be less, but the number of instructions actually executed by the processor depends on the loop count. Getting your point here? So whenever we are dealing with the loop instruction used in a program, the number of instructions may be less, but the number of instructions actually executed depends on the count of the loop. Getting your point here? With the help of a count register, with the help of a CX register. The procedure for generating delays using a microprocessor is as follows. So the first step is you need to determine what the exact delay required. First, we determine at what delay the processor should execute. Next, second is select the instructions for delay loop. Select the instructions for the delay loop. So while selecting the instructions, care should be taken that the execution of these instructions does not interfere with the main program execution. Getting your point here? So while selecting the instructions, you should take care, you should keep in mind that the execution of these instructions which are in the delay loop does not interfere with the main program execution. That is, any program, any memory location or register used by the main program must not be modified by the delay routine. So whatever the memory location, whatever the registers we are using by the main program, it should not be modified by the delay program. The instructions executed for the delay loop are dummy instructions in the sense that the result of those instructions is useless. But the time required for their execution, nothing but going to the count, again the same instructions, is an elemental part of the required delay. Getting a point here? So delay loop consists of some instructions, some dummy instructions whose result of those instructions are useless, but the thing is the time required for that execution is elemental part of the required delay. Getting a point here? So first the thing is we need to determine the exact delay required and we need to select the instructions in for delay loop. So in order to select, while selecting the instructions, you need to take care of that the execution of this instruction should not interfere with the main program execution. That is nothing but if you are using some memory locations or the register which are used by the main program must not be modified by the delay routine. They are just the dummy instructions. This to calculate the number of the total delay, we have to use that instructions. So as we need to find out the number of clock states required for the execution of each of the instructions in the loop, then find out the clock states required, which is n, small n, to execute the loop once by adding all the clock states required to execute the instructions individually and sum it up. Then find out the period of the clock frequency at which the processor is running, that is duration of the clock state, capital T. Find out the time required for the execution of the loop once by multiplying with the period time with the number of clock states required, small n, to execute the delay loop once. Then find out the count n by dividing the required time delay by the duration for the execution of the loop once n into t. Then if you are getting the count, then it may not be possible to generate the exact time delays using this method, but the delays obtained using this method are sufficiently accurate to be used in most of the practical problems. So for more accurate delays, a programmable timer or counter chip 8253 or 8254 may be used. So the formula is count. In order to find out the count of number of clock pulses required, or the count is equal to required delay, which is Td by n into t. So for that one we need to find out Td, which is the required delay, where we are finding out determining the actual delay required, or the delay required by the processor. Then n into t, n is the total number of clock states required and t is the clock period, nothing but one clock pulse, which is inverse of the clock frequency. We will take one example. Suppose write a program to generate a delay of 100 milliseconds using an 8086 system that runs on 10 MHz frequency. So these are the instructions what we have written a program to generate a delay of 100 milliseconds. Okay, move cx comma count, label, declaring a label loop, decrement cx, no operation, jump if non-zero, again to label. So for first one, move count 4, label is a loop 2, no operation 3, and jump if non-zero label 16. So these are the states, these are the clock pulses required for execution. So as we are going for we are going for only loop execution. So number of clock cycles for label loop is, so this is not included in the label, so it will be 2 plus 3 plus 16, total is equal to 21. Getting a point here? The number of clock cycles for execution in the loop, because they are being looped number of times, right? Now the instruction move cx comma count does not comes into the delay loop, yes or no? The time required for execution of the loop once Once means n into t. What is n here? Number of states. T is clock period, which is 1 by time period, 1 by clock frequency. Now here what is the clock frequency now? 10 megahertz. If I do the inverse of 10 megahertz, you will get as 0.1 microseconds. So no, 0.1 microseconds. So now multiplied with the 21, we will get as 2.1 microseconds. This is the time required for execution of the loop once. Now count n is equal to required delay Td by n into t. Now required delay is given as 100 milliseconds by n into t is 2.1 microseconds, which is given as 47619 is the count n value for this corresponding instruction. So in hexadecimal it will be given as 0BA03H. Right? So this is the count of the clock pulses required in order to generate a delay of 100 milliseconds that runs on 10 megahertz frequency. Clear or not? We'll see the actual time delay, exact time delay. So this is the program how it is being written as cx comma count. So BA03. This is the count value. This is the loop. The program has been written. So number of states is this. So return H again. So now first thing is count, which is Cx. So I need to multiply with n into t. So now here t is 4 and 0.1 is time period or clock period. 0.1 into 4 plus first and second, this is 2 plus 3 into the total number of count, which is 47619 into 0.1 plus 16 into count minus 1, which is 4761H into 0.1 plus again coming to count 4 into 0.1 plus the last 8 into 0.1. So if you do all these things, see here first 4 into 0.1 plus 2.2 plus 3 into 0.1 into 47619, which is the count value what we have calculated before, plus 16 into 4768 minus 1, next count is minus 1 into, as we are into 0.1 and plus again going to count, which is 4 into 0.1 plus 8 into 0.1, which gives the value of 100 milliseconds, which the generation of 100 milliseconds delay. Clear? This is how you will be generating the delay for a certain clock frequency. Next example, this is for delay of 10 minutes. So required time delay is 10 minutes, which is 600 seconds. Clock frequency 10 megahertz. Time is 0.1 microseconds. So there will be a two nested loops for decrementing the two counting registers, decrement Cx, decrement Bx. Let the first loop has a count, second count. So T1 will get as, it is not bar, it is plus 2 plus 3 plus 16. Decrement Bx is 2 plus 3 plus 16 and decrement Ax is 16 plus 2. Decrement Bx is 16 plus 2, decrement Cx is 2 plus 3 plus 16 into count is 0 triple F, which is 6553635 into 0.1 which is 0.137605, which will be counted 0.137605 plus 16 plus 2 into 10 power minus 6 into 0.1, which is 1 megahertz, 0.1 microseconds, which is 0.1376068. Time delay is 10 into 60, 600 seconds. So count is equal to 600 by 0.1376068, which is 4359.58, which is 4360, which is 1107H. So like this, you will be calculating the count, number of clock pulses required for generating the delay, and you can match with the actual delay being required. Thank you.